Okay, so we're still working with limits. We're still hoping to be able to use direct substitution if we can. If you remember that list from one of the previous videos about all the different topics or all the different techniques I'm going to show you, one of the techniques on there is rationalizing numerators, or I think I might just say rationalizing. We're going to look at rationalizing numerators and what I call clearing little fractions, which really isn't the correct way to do it, but it seems to click with students that they remember what they're supposed to do if I call it that. So if I look at example 1, I'm not even going to worry about the directions yet. If I were just asked to find this limit, my first instinct would be to try using direct substitution. But notice that when I plug the 0 in, I end up with the square root of 1 minus 1, which gives me 0 over 0, which remember is my indeterminate form and is completely meaningless. So since that didn't work, I'm going to go ahead and erase that. And now I want to think of another way that I can rewrite this function because I'm really hoping that I can plug 0 in. I would really like to use direct substitution. Well, if you think back to previous math courses, we would run into situations where we would have radicals in the denominator, and we'd have to try to figure out a way to rewrite the function to get the radical out of the denominator because it wasn't really considered the most proper form. Well, in doing so, we would change the look of our expression. Well, if my goal here is to rewrite my function in another way so that I can hopefully plug 0 in, why don't I try doing what I did in my previous math course, only instead of trying to rationalize the denominator by getting rid of the radical, what if I try to rationalize the numerator? It might not put my equation or my expression in simplest form, but maybe it'll give me an option to plug in. So if I think back to my previous math courses, in order to rationalize the denominator, I'd have to multiply top and bottom by the conjugate. So I'm going to try to multiply top and bottom here by the conjugate. So remember, conjugate means it changes only by that middle sign. So I'm going to say that this is the same thing as the square root of x plus 1. But if I multiply that by the top, in order to not change my expression, I also have to multiply it on the bottom. Well, on top, I notice I'm in the form a minus b times a plus b. Well, if I have a minus b times a plus b, I know that's going to give me a squared minus b squared. And I'm going to go ahead and leave the bottom in this multiplication form. I'm going to wait to distribute. Because what I'm hoping is that as my function changes a little bit in its look, maybe I can cancel some things out. Because remember, it's this x right here that's causing the 0 in the denominator. So now from here, if I square x plus 1, that square root goes away. I end up with x plus 1 minus 1 all over x times the square root of x plus 1 plus 1. Well, notice that that allows me to combine my 1 and minus 1. They're going to combine to be 0, and I'm going to be left with x over x. Those are going to reduce then, leaving me with 1, because I have to have something on top, over the square root of x plus 1 plus 1. And now I check to see if I can use direct substitution, because the limit, I'm going to go ahead and squeeze that in there, as x approaches 0 of this new function that is just like this function, except it looks different because it no longer has a domain restriction of 0. So even though this function has something going on at 0, be it a whole or something that's not allowing me to actually evaluate that 0, this function I can evaluate it for, and these will be the same except at that one little spot. And since I don't really care what's happening there, only what happens as I get close to it, I'm going to go ahead and do that direct substitution, and I'm going to get 1 over 0 plus 1 is the square root of 1 plus 1, which gives me 1/2 for my limit. And I can always check and look and see what that looks like. If I wanted to, I could graph my given function and zoom in and see what is really happening as x approaches 0. So that's what it means to rationalize a numerator. Now let's look at the idea of clearing little fractions. Okay, so I'm going to rationalize here by getting rid of my little fractions. So once again, my first instinct is to try direct substitution. When I do, I end up with 1 over 7 minus 1 over 7 all over 0. Well, isn't that just going to give me 0 over 0? And isn't that meaningless? So direct substitution again doesn't work. So I again want to figure out how can I rewrite this function and maybe make it so direct substitution does work. Well, I know I've learned in the past that it's awkward to have little fractions inside of one big fraction, so maybe I'll try to clear those little fractions. The way I'm going to do that is I'm going to multiply, and I'm going to write this out, so I'm going to multiply top and bottom of the whole thing by the least common denominator. I'm going to write LCD of the little fractions. Well, remember, I can find a common denominator by multiplying two numbers together. For example, a common denominator between 5 and 3 is 15. It just also happens to be the least. A common denominator between 4 and 6 is 24. It's not the least common denominator, but it's a common denominator. So my least common denominator between x plus 7 and 7, I can get by multiplying them together. If it wasn't my least common denominator, it would still work. And we can look at techniques in class on how to find the least common denominator if that's something you're unsure of as you work through different problems like this. So now I'm going to multiply the entire top by my least common denominator. So what I do when I multiply the entire top by that, it distributes in to both of them. So I'm going to have 7x plus 7 times 1 over x plus 7 minus 1 over 7 times 7 times x plus 7. And then I'm going to multiply the bottom by it. So I'll have 7 times x plus 7 times x. Well, before I do anything else, I'm going to notice that this is really helpful because it gets rid of my little fractions. If you do it right, they should cancel. Again, I'm going to leave my bottom in that factored form. And on top, I see I'm left with 7 times 1 minus, and this minus 1 is going to distribute in here. So minus 1 times x is minus x. Minus 1 times 7 is minus 7. All over, and it doesn't matter where I put the x, so I'm going to say 7x times x plus 7. I still can't use direct substitution, but what I can do is I can combine 7 and minus 7. They're going to become 0. And then I'm also going to be allowed to cancel my x's, leaving me with, instead of the limit of my original function, the limit as x approaches 0 of negative 1 is left on top, 7 times x plus 7 is left on the bottom, and guess what? Now I can use direct substitution. So using direct substitution, I plug my 0 in, and my limit is negative 1 over 7 times 7, or negative 1 over 49. So two separate ways to, again, rewrite a function. So now we've learned we can rewrite a function by factoring. If you can't factor, which I could not factor this first one, but you do have a radical involved, maybe you could try rationalizing by multiplying top and bottom by a conjugate. If that doesn't work, and you have some little fractions involved, maybe you can try rationalizing or rewriting your function by getting rid of the little fractions. How do I do that? By multiplying top and bottom of my original fraction, so top and bottom, by the least common denominator of those little fractions. But the big thing is my goal in all of this and all of my rewriting is to be able to use direct substitution to help me determine my limit.